Okay, X-rays. First question. Why is ultrasound used to scan unborn babies but X-rays are not? Well, looking at the answer scheme, just saying that X-rays are harmful to the baby is not good enough. You have to say that X-rays are ionizing. Okay? Ionizing. Otherwise you don't get the marks. So, X-rays are ionizing, and then say, therefore, they're harmful to the baby. And give an example. If they're ionizing, they will increase the baby's risk of getting cancer, for example. Okay? And then, to get all the marks, go on to say that ultrasound is not ionizing and ultrasound is not harmful to the baby. Okay, next question. How does an ultrasound wave produce an image from a boundary between two materials? 2 marks. Okay, so you've got a boundary between two materials, I don't know, muscle and bone maybe. The ultrasound wave comes in here and use the phrase, it's partially reflected. Okay, some of it continues, but some of it is reflected back. So partially reflected. Okay? Partially reflected by the boundary between the two materials. Next, say that the time taken from the original wave leaving the transmitter, being the partially reflected wave getting back to the detector, which is next to the transmitter in the thing that they hold, the time taken is measured and you can work out the distance of the boundary from that time. Okay. Next. Right, it's this thing here. They've told us that you've got the baby here, okay, inside the mother, and there's the outside of the mother, and the ultrasound thing that the nurse holds, that is 4 centimeters from the baby, okay? Now the transmitter and the detector are both in the jobby thing, the ultrasound device. That is the transmitted pulse from the ultrasound thing, and that's the reflected pulse that's detected in the thing as well. So it goes boing, boing, transmitted, detected. We have to work out the speed that that wave travels, that the ultrasound pulse travels. So, to get full marks in this question, don't forget that it's travelled there and back again. That's important. So it's travelled a total distance of 8 centimetres. Okay, don't forget that. So we're just using speed as distance over time. So speed is distance over time. So distance, 8 centimetres. Now they want the answer in metres per second, so we've got to put it into metres. Centimetres into metres is 0.08. Or 8 times 10 to the minus 2, it's up to you. Time, so it's travelled a distance of 8 centimetres in 80 minus 30, so 50 times 10 to the minus 6 seconds. That's in metres, that's got to be in seconds. Okay? Stick that in your calculator and you get 1,600 meters per second. Right. Now, as always, just pause for a second and ask yourself, is that a sensible answer? Yes, it is, because the speed of sound in water is about 1,500 meters per second, so it's very close. And human flesh, we're about 60% water, so seems sensible. The speed of sound in air is about 330 meters per second. In solids, it's faster. So again, that seems sensible. Good, okay, what's next? How do X-rays produce an image? 3 marks. Right, so there's an X-ray of a broken arm. How do you get 3 marks out of this? Well, X-rays work differently to sound waves and ultrasound waves. Okay, first mark. The bones absorb the X-rays. Okay? Second mark. Soft tissue transmits the X-rays. It absorbs them slightly, but nowhere near as much as bone. Third mark. The X-ray transmitter is on one side of the arm, the detector is on the other. So use the word transmitted, the transmitted X-rays are detected by the detector on the other side of the arm. And that's where you get the image from. Okay, good. Next. Right, complete the sentence. X-rays are able to produce detailed images because their wavelength is very what? The wavelength of X-rays is very short or small. Either will get you the marks. X-rays are part of the electromagnetic spectrum and they're at the short wavelength end. And their wavelength is about 10 picometers to about 10 nanometers, roughly. It's X-rays. Okay, so that's 10 to the minus 11 meters to 10 to the minus 8 meters. So that's 100 billionth of a meter, and that's 100 millionth of a meter. So really, really small. And that means they have a high energy, and that's why they can penetrate matter so well. Okay, there we go. I think that's everything. Yeah. Brilliant.